Good morning, Dr. Sobchak. Are you there? Good morning, Mrs.
Good morning, Professor. How are you?
I'm fine, thank you. I'm sorry we had some confusion about the date of the meeting yesterday.
It is my fault because I forgot the agreement that we had for changing the day. Then
Yes.
I only get with the custom to connect
Yes.
on Wednesday, and then sorry about the confusion, but
No problem. I also was a little bit confused because I ended up having another appointment that I have to go to in about an hour and hour and a half from now. I have to leave the meeting, but if certainly can continue discussions without me, and I will view the recording afterwards.
Okay, yeah. Okay, not a problem for me. Okay, yeah. Professor Garrett.
Yes, he seems to be here, but I haven't yet seen him or heard anything from him.
Okay.
Also, I think I did get an email from Brian. Brian is his name?
Brian, yes.
Yes. Yeah, he did ask about the link to the meeting, but I think he was able to connect. At least I saw that he was connected yesterday for a short time.
Yes, he was connected yesterday. I don't know why he's lost in the link for today. I hope he can connect. Yes.
Yes. Okay. But maybe he has other commitments.
Yeah.
So I did receive some emails from Garrett Sobchak, but I didn't really have an opportunity to reply to them. Perhaps I hope he can discuss some of his ideas today. From Garrett, from Dr. Sobchak.
Okay, yeah. Yeah.
Yes, he had some comments about the relationship between category theory and geometry, and I think I didn't take the time to write my thoughts in an email, but
yeah. But those mail were sent by Professor Sobchak before yesterday.
Yes.
Few
weeks,
a
few weeks ago. Yes, I think. But, I think he's now currently in Mexico, I believe. But he was traveling, I think, in a week ago or 2 weeks ago.
Yes, by now I think he's in Mexico, in Cholula.
Ah, yes.
Yes.
Okay.
It is not too much far from here, but not. It's not possible to visit. Not easy to
Yeah.
visit this place. Yeah.
I noticed that the weather in Mexico has been continued to be rather cool.
Yes.
Cool.
Those this day, the past weeks was too much cold, too much
Yeah.
cold. This kind of weather is not more too much usual in Mexico.
Yeah. Yeah.
But I think we need to get accustomed for this.
Yeah, you never know. Like, things do change over time. And
Yes.
here the weather is cold, but it's expected. But otherwise pleasant, like not so bad. So
Yeah.
it's within the range of normal for here.
Oh, okay. In this time of year, it's used to get too much rain and
Usually not rain, but
uh,
often a lot of snow.
oh,
Like
okay.
it's
Mm.
equivalent of rain, but
Yeah. Mm.
but over the time of the line December, the late December, a few weeks ago, we did have an unusual amount of rain. It was warm and we had an unusual amount of rain, and if that had been uh, snow instead of rain, then
Oh,
it would be very unpleasant here right now with too much snow.
oh,
But now today, not so bad. Even I can see green grass here, and that
oh,
seems unusual, at least pleasant for this time of year.
oh.
Yeah. Okay. Well, um, we could perhaps officially start the meeting. I see some message here.
Maybe
Maybe.
we can send a
Oh,
message by chat to Professor.
oh, yes, I think so. He says he sent me an email. It says Zoom says that host is not letting me unmute. Hmm, that's odd. Uh,
Okay.
Let me see if I can solve that problem. Well, okay. Hmm. Hmm. I don't see any problem. Oh, he's seems to have just disconnected.
It's connected now. Yeah.
Disconnect. He logged out. Perhaps he's going to try again. Let's see. Hmm. I just sent him a message to suggest that he try again. Um,
Yes.
Perhaps he had some problem.
Maybe he had some problem because I think that he started the conference and tried to start it again, and then
Mm.
okay.
Okay.
And
Did you have some? I'm sorry. Did you have some slides or discussion you wanted to
no,
share?
I did try to write some slides, but I don't get too much for this. Um, um, because some of these ideas that I wanted to um, to present were present in another sessions of seminar.
Mm-hmm.
I like it to fix the idea of around the definition of algebras, of Clifford algebras. And
Mm-hmm.
after of this, I think that we need to have a definition of duality, because I
Yes.
don't understand yet the concept of duality of Professor Sobsik. Um, then I think that we are speaking in different way about
Mm-hmm.
the duality concept, and then I think that we need to fix first those ideas, and then maybe we can work on on that. But
Well, I think like it did seem to me important to, as you say, to define clearly what duality we're talking about, because I think that there are many possible dualities, um, and the kind of duality that we see, like inherent in category theory, um, is of a different nature, for example, than the uh, say the apparent duality between, say, space and time, or between the like the different parts of a Lorentz metric, for example.
yeah,
Um, but somehow that is connected with the more apparent kind of duality between vectors and covectors, for example.
yeah,
And so what occurred to me was that it's this was a subject that uh, Zbigniew thought was quite important. And in one of the last papers that he wrote, he discussed the creation and evaluation operators,
yeah,
and the fact that they could be used to form idempotent uh, that would split and like basically split an expression into a space-like part and a time-like part.
yeah,
And but this was sort of a structure built on top of the notion of vectors and covectors, or vectors and forms. And it, in a sense, it's a, I was always intrigued by the fact that this was seemed to be a way to introduce the so the difference between space and time in a completely sort of algebraic way. Right? So it's in a way that does not involve any metric notions. So one would say that it doesn't involve any assumptions about geometry as such. And so we don't need to worry about Lorentz metrics or
Yeah.
calling a vector time-like versus space-like and so forth. All of that mechanism sort of goes away. And so it's sort of from a deeper level, there is this kind of structure of space and time that arises algebraically. And so maybe something like that is related to what Dr. Sobczak is talking about. But to me, it's still not that clear.
Yeah. I can see that Professor Garrett get connected yet, but I don't know if he is.
Yeah, I don't know. I will try chat too. I tried to send him a chat. He hasn't replied. I just sent him another email. He asked me to send him a link, so I think I can do that. Invite. Oh, technology. Now I see him connected here twice. We have some success.
Okay.
No audio yet, but I see a video. Hmm. Perhaps he has two different computers.
Maybe the cellular and phone and a computer.
Yes, or a cell phone. Yes. Hmm. Oh, no.
We lost what?
Lost both now. I don't know what's happening. I was going to see if I could find that the paper by Zbigniew. I have it here somewhere. I haven't looked at it for quite a while, but it was the paper about the center of mass or center of inertia.
The paper, Osiewicz paper.
Yes.
Mm.
I know I have it here somewhere. Yeah. Center of inertia. Yeah. Oh, that's one of the papers. That's not the one I was thinking of. Mass center. Maybe it's this one. Yes, that looks familiar. Okay. Mini body mass center for finite speed radiation. Yeah. That one was published in Journal of Physics in 2014. I think a shorter version of the one that I have here. But if I can find the one particular spot. Yes, it's these. It's a rather long paper, so it's the ideas are uh, presented sort of at different levels in different ways. I think this paper was written more for mathematicians and not so much for physicists, but it.
Yeah.
Let's see if I don't see. I'm just checking on whether Dr. Sobchak has sent me an email. If no, still nothing. I could share this PDF document
Okay.
so that I could point to the part that I remember. I'm not well organized to do this at this point, but still, I'm sure you will remember this paper when you see it.
I saw this paper sometimes, but I not remember now his content.
Okay, let's take a look at this one here.
Okay.
And so he has these operators that are defined in terms of evaluation and creation.
Okay.
But they have a particular symmetry to them that
Yeah.
and it is defined over the over both Grassmann algebras, the
Yes.
Grassmann algebra of vectors and Grassmann algebra of forms. And as usual, this evaluation operator is like insertion in exterior algebra.
Yeah.
So it is a linear operator. It's nilpotent, I think, so that, of course, if you insert the same vector twice into a differential form, by form, two form, then the result is zero. Right? Let me return just to
Here is, I think you paste the definition. Oh, no, it is here.
Yeah, I've moved here a bit.
Sorry.
Just wanted to. Yeah, so here at this equation 1.3.6 is showing that evaluation is nilpotent. And creation is also nilpotent operator. Right?
Yeah.
Because it's a Grassmann algebra. Right?
Yes. It is similar to the definitions that we used in the Frolinger and Nijenko's algebras. Yes.
Yes.
Here, there we used some definitions for going into the different degree, Grassmann degree algebra. And I remember we found some properties of these operators, and those are related with the duality concept. Concept. And not only that, but and I think that we can see that because this is related with the pullback operation. I think it is in the third arrow. Maybe it is up, or this notation is for the dual. I don't understand. In pi, he is in notation of the algebra.
Yes, pi is an idempotent operator that's a composition of two nilpotents, right?
Yeah. Uh-huh.
And D also is a nilpotent operator, but it's a composition of the same operators but in a different order, right?
Okay. Uh-huh.
So in the first case, you do this creation operation and then you do evaluation. But in the other case, you do evaluation first and then the creation.
Yeah. Uh-huh.
And and these two compositions of nilpotent operators, give rise to these idempotent operators, and then the pi operator is associated with the space-like part of the split, and the D operator is associated with the time-like part of the split.
Uh-huh.
But it's subtle in some respects. It seems simple, but in fact, there's some algebraic subtlety here. In particular, the algebra lets you distinguish between the properties of space and the properties of time. It's quite, I think, quite quite interesting how that works out. That in the case of the D operator, you end up with this ideal, but in the space operator, it's just an algebra map, right? You're just mapping from space-time into space. So so you have that mapping, but when you map space-time into time, it has a different structure. So it to me, it's I don't know quite what how to interpret these algebraic concepts in terms of physics, but it seems intriguing that it might be possible to do that.
I have in some slide here the definition of those of operators in only algebraic way. And after those operators are used to split space-time, and then the spatial component of a differential form and the time component of that differential form. I think that those are related with these expressions that are here.
Yes. There, of course, are more details here. But ultimately, the goal in this paper is to define a relative velocity, right? As a space-like vector in a completely algebraic way without any reference to geometry. So it's geometry, as Ushevich always insisted. I think that geometry is only about the mapping between vectors to covectors, right? It's like, so that the only thing that distinguishes geometry from algebra is the fact that you have this mapping that is given between vectors and covectors. And so we usually just refer to that as the metric. And in most formulations of geometry, one talks directly about scalar products, but it misses some of the algebraic structure. If the only thing you're interested in are quadratic forms or scalar products, then you miss some of these properties, or the properties end up in a somewhat different form, so where you have like linear space, linear vector space, and its dual vector space. So this here, like Dr. Sobchak was doing, here in this formulation, you start with the duality sort of built in at the beginning, right? You say that we have vectors and we have forms, and they are two different Grassmann algebras, but they have this relationship between them, this relationship of evaluation, and that's a kind of an algebraic property as opposed to saying that it's a function of the geometry, or that it's a there isn't even any need really to talk about it in terms of like functionals, for example. So I'm not sure. I see Dr. Sobchak is returned.
Okay.
I don't know if he is seeing us or not. Where is my? I should, in principle, be able. Okay, I'll send him a chat message. So I sent him a message. Oh, I don't know what's happening. He's connected, but his microphone is listed as off, and his video is just the avatar. Oh.
But now I only see one connection of Professor Garrett.
Oh, do you?
Yeah.
Oh, I see two. We could perhaps restart the entire meeting and try.
Maybe.
Try that.
We can leave and.
Yes, and try again.
Yeah.
Stop sharing. I really don't know here. Let's see, what else can I do? Okay, put in the meeting room.
Okay, here Garrett
Admit.
lost his connection.
Ah, that looks
Uh,
better. Oh, maybe. I see the
again.
microphone going off and on.
Okay, so I'm on my tablet again. For some reason, I cannot log in on my computer. I don't know why. It's saying, it says host will not allow me to unmute. But I'm on my tablet. Can you hear me now? I'm speaking on my
Yes.
tablet.
Yes.
Looks, I can't use my computer. I'm in Cholula. So
Ah,
I had to reinstall Zoom, first of all, and then this audio, for some reason, I can't unmute it says every time I try to unmute, it says host will not allow me to unmute. So I did have some things I wanted to share on my screen regarding this Fano plane, but I'm not sure I can do that with the way things are now. I'm on my tablet now.
okay. On my side, oh, there you are.
We can see
Uh,
you.
on my
Yeah,
side,
I'm also using a hotspot, so I don't want to use up all my space with the video. But if I could show slides, it would be good. But I'm on my tablet now. For some reason, I cannot get the computer to unmute. Well, it says you're not letting me unmute, but it's just something not set up right or something. At my side, I'm sure that's the problem.
on my side, it only shows that I can ask you to unmute, but I don't have any function to either
Yeah.
stop you from muting or
Well,
not.
so that's what I do. I say you ask me to unmute, and I say unmute, and then it tells me host will not allow you to unmute.
That's seriously confusing.
But I can hear you. I can participate on my tablet. But I wanted to show you. I'm really excited about what I've discovered about this Fano plane, and I think I've clarified the notion of local duality in a way that's really very nice, I think. But I can't. I wish I could show you some of the things I have on my computer, but I don't have them on my tablet here. But at least the tablet works. So
That's oh well.
let's see what I have here. I'll try to. Yeah, I'm using a hotspot too, which can be problematic as well. But let's see. But before, when I was using my tablet, I was able to look at you on my computer as well, which was strange. I didn't understand what was going on. So I turned off my tablet and then it stopped working again. So I can, but I'm going to try to look at what I can do. Maybe I can somehow get on the computer at the same time with the tablet or so. I don't know what was going on there.
Hmm.
Pretty strange though. I'm going to try to log in
Yes.
again on my computer with my tablet on.
Sure. Okay.
All right, let me try that. See what happens here. I did restart the computer, which took some time because I had. Okay, let's see. You said you sent me a link. I'm looking for that link, but I'm
I
going
can
back
send you
to the
another.
old link. Okay, can you send me another one right away?
Sure.
It gets mixed in with the other message. Well, let's see. Maybe I can get it now.
Let's see. Invite. Yeah. There. Okay.
Okay, I said join. Let's see what happens.
Hmm. There you are again.
Okay, join with computer audio.
Well, now you have two audios.
Okay, can you hear me now?
Yeah, except that I think you have some feedback.
Yeah. For some, I'm using my tablet and my computer at the same time, which is strange, of course.
You need to put off the audio in one, and
Oh yeah.
anyway, you need to slow all the microphone and audio in one of your equipos. One of in maybe in your computer you can put off the audio, and in your tablet you can use for communication.
Okay, of course now both are off, so we cannot hear him speaking.
Okay, can you hear me now?
Yes.
Yes, good. Mhm. Mhm.
Okay. Okay, let me see if I can get to my um, okay, I want to. That's pretty strange what's happening, why it's doing that, but anyway. Let's see, now I want to,
Yeah, if you could share this screen, that would be okay, I guess.
okay,
I'll let
let
you
me
do that.
just get to where my pages are, and then I'll share the screen. Okay, let's see.
We cannot see video from your computer either.
Okay, I'll turn that in a minute. Let me try to get what I'm looking for here.
Sure.
Okay, let's see where's okay, this should do it. Okay. Okay, I'm going to try to share my screen now. If I can get back to the other page here. Okay, here we are.
So I do.
Can you see that?
I see something here. It's figure 2 JPEG.
Yeah, maybe I can fix it. I can. I've got too many screens open. How do I fix that?
You'll have to turn off one microphone too.
Okay. Maybe I have to try.
It's usually best to have the microphone and the speaker on the same machine.
Yeah. Let's see. I can't see my. Oh, okay. There I can. Okay. Okay. Can you still see my screen?
Yes, I can still see what you're showing. I don't see any video. But
Can you hear me still?
Yes,
Can you hear me?
yeah, it sounds fine.
Mhm.
Yes,
Okay, I can. Okay, you can't see that what I've put on the screen though, right?
I can see. Yes.
Okay, well, So you see the circle and the triangle inside the circle, right?
Yeah,
Or not? What do you
yes,
see
I
anything?
mean yes, I see a red circle and I see a triangle. The triangle is not entirely inside the circle.
Yeah, well, it should be. That's the thing. That point at the North Pole should be. My perspective is bad on this picture, but I didn't have enough time to put a different picture in. But the idea is that that's the plane at the on the equator of the circle of the sphere. That's the so-called Fano plane. But it's bad. I have a better picture, but I didn't have enough time because I had to reload the Zoom version and all kinds of stuff to try to get on this morning now. And late yesterday, we were busy trying to handle some things we have to do at this end. But anyway, uh, I was interested in whether Dr. Cruz was able to make any headway with understanding what I call local duality. That's the other important idea, which allows me to basically name all the points in the plane with null vectors, which is rather strange, but I think I have a simple explanation of that, which I probably won't be able to explain very well today. But Jesus, were you able to make any progress on what I'd like to do is show that this is a way of replacing some of the ideas which you do in category theory with geometric algebra of the in the final plane, actually. But we really haven't had much time to talk more about that. But Jesus, can you hear me, Dr. Cruz?
Yes, I can hear you. Yes.
I'm still very excited about these ideas. I'm talking to a couple of engineers from Volkswagen. So the basic idea is that you use null vectors to name all the points in any direction. a ray is just like a beam of light. A ray has a direction in one singularity, but it has no length. So it's a generalization of the concept of a vector. A ray just encapsulates the idea of a direction, a ray, like a ray of light on the light cone. You should always think of a ray as just being a point on the light cone. Of course, for every line on the light cone, you have an infinite dimensional ray, okay? So pick any dimension, you name all the directions in space and in hyperdimensions with a single null vector. And you can say that null vector represents, it's an oriented null vector, which means it has a positive orientation. And if you change the sign of the null vector, then it's the negative orientation. So a ray is an oriented line segment, but it has no length because it's a null vector. A null vector has square 0. So
what do you mean by what can you mean by change the sign?
Null vector. Pardon?
What do you mean by change the sign of a null vector?
Well, like a ray has two directions. You put an arrow on the ray, that's the positive direction. If you say negative, then it changes, then it goes the opposite direction. Okay, so a ray, then we think of a ray as pointing upward. Then the negative of that ray points downward, but it's the same direction. So a ray encapsulates the idea of direction. Now you can think about a ray as being in any direction in space. So any null vectors you pick out, you can represent R1, just the x-axis, if you like, by a ray pointing in that direction of the x-axis. And okay, the positive real numbers are on the pot. You have to pick an origin. That's the singularity point. Okay, so a ray then, you think about a ray as one point is left out. The ray array, okay, and that's the origin. So again, it's arbitrary. You have array is just an infinite line segment with one point left out. And that's the point you choose for the origin. Or you can choose any point along the array as the origin. So the idea then is each line on the null cone represents a direction in space. Well, but actually, okay, so that's the first thing. So a single null vector represents a direction, like up or down or to the left or right, or in any number of dimensions. You don't have to say what dimension it's in. Array is just the abstract concept of a direction, a direct oriented direction. So it can have, if you choose array, it either could choose it going up or down, or you assign the direction you want to choose to it. That's the basic idea. So a single null vector or a single point on the light cone represents a direction, a unique direction. And you can choose that direction to be, I'm thinking of a one-dimensional light cone. A one-dimensional light cone is just a single ray, okay? And you leave out one point because if you think about a ray, it's kind of like a projection. It can be a circle going to infinity and back. So a ray you can think about as being a circle. And that's the idea of the spannel plane, that the circle they choose in the center of the plane is really at infinity, or it's at
we lost your audio, Professor.
Seemed okay. Oops. It's share disappeared. And now both are mute.
okay. Can you hear me now?
Yes, now, yes.
Okay, so I'm sorry that this computer is not quite up to date. But okay, I'm going to try to. Okay, okay, I've muted one side again. Can you hear me? Can you still hear me?
Yes,
that's fine.
Yes.
Okay. So again, I was talking about array. Array is just a direction you can think about as on the light cone, but it can be any direction in any number of dimensions then. But it's an oriented ray. So a ray has a direction. Now, if you change the sign of the null vector representing the ray, it points in the other direction. And that's the only two things we're abstracting with a null vector. And you can think about the null vector as lying on a light cone. That's the way it originated with Einstein, back in with Minkowski space-time. They thought about rays as being on the light cone. But before Einstein, that was the time of Gibbs Heaviside and those guys, and tensor analysis, all those things. I think what led MacLean to invent category theory was the absence of this idea of local duality, which is the idea that I'm trying to explain to you right now. I think I finally, just since coming to Mexico now, it's dawned on me, I think I can solve all the problems now. And the key idea was looking at this Fano plane, because the Fano plane uses the so-called two p-adic number to represent. Well, he takes a group algebra of the two p-adic numbers and basically represents using this concept of global duality, which they have no other way of doing it. With the concept of local duality, you don't have to use this group algebra that they're always talking about. That follows from having to use what I call global duality. But if you I could explain better if I maybe if we can meet in another week, I can resolve these problems I'm having here.
Professor Garrett, but when you say the duality here, what are dual?
Okay,
objects.
Okay, the dual
What are
objects
the-
are exactly in two-dimensional space. The dual objects are the two 45-degree angle rays that go out into space. Okay, so the two-dimensional light cone, you have two null vectors, one going off to the right, one going off to the left, making 45 degrees. Is that, you understand that, right? A light cone in two-dimensional space is just, well, then you have the hyperbolas. You know, you take two diagonal lines meeting at the origin, the 0 point, and you have the hyperbolas. There's the four branches of hyperbolas. And so in two-dimensional space, you have two, globally speaking, you have two directions. The horizontal rays going off in the two-dimensional plane. There's only two null vectors, namely one going off to the right, one going off to the left horizontally. And then the axis represents E1 squared, or we think about E1 squared going vertically, and then F1 is going horizontally then. Okay, so globally, you have two null vectors involved, and they do satisfy that property. C1 dot C2 is equal to 1/2, and that's the same thing as saying C1 times C2 minus C2 times C1 is equal to 1. Okay?
We lost your screen that
Sure,
you
yeah.
share with us.
Okay, I can share screen again here. Maybe
Please.
it's still there. Let's see here. This one. Can you see that now?
Yes.
Yes.
If I understood, okay, the red one circle represents one sphere in three-dimensional space.
Yeah, so really just think about the triangle in the center. That's on the equator of the sphere, plane passing through the equator.
Okay, in the plane, in the triangle, I don't not understand if it is in the vertical plane or it is in the horizontal plane.
It's in the horizontal plane. It's a bad picture. I have another one, but I haven't been able to. I'd have to download it from my email, and then I have to change it to a PDF file, and I haven't done that yet. So that's the problem with that. So I'm using this old picture I have here. It's not a good picture at all, but you can see I'm naming points with these null vectors, C1, C2, C3. So yeah, I really, can we meet again next week? I could try to organize these things much better and give a much better presentation, because like I say, I'd like you to think about just R2. R2 is defined by two null vectors which cross at whatever points you want them to cross. They have to have a joint point in common called the origin, but it can be any point. So you have two rays in space. You can choose whatever direction you want for those rays, but there's two rays. Normally in R2, you choose two rays which are diagonals, and then the axes then are the upper axis is E1, and the horizontal axis is the x-axis F1. But the rays then go off at 45 degrees. But now, if you consider in three-dimensional space, you can think about a plane cutting the sphere. If you take the plane, let's see here. Okay, take a light cone in three-dimensional space. So it's defined by three null vectors going off at 120 degrees with respect to each other. So you can think about the light cone in three-dimensional space as three null vectors going off in three directions. That's a basis for the geometric algebra 1, 2. We define three null vectors going off at 120 degrees with each other. That's the typical light cone in physics, is it not? that's true, is it? You agree? So you can choose three vectors in three-dimensional space. You don't have to think about the Fano plane here. Think about a sphere and take three vectors from the origin of the sphere going off at 120 degrees. They define the light cone then, going up from the origin of the sphere. Or you can take it at the South Pole, which is what I would like to do if I have more time to make everything that I have to make to do that. But can you understand what I'm saying? So a light cone in three-dimensional space is defined by three null vectors going off at 120 degrees. You can take that from the origin of the sphere, choose 3 points that are equally distanced on the light cone. And those define three null vectors, C1, C2, and C3. Or in any number of dimensions. Now, then you can think about planes cutting that sphere. A plane will cut a sphere in what? Well, if that plane passes through the origin of the sphere, it'll define a line, right? Or if you take a vertical plane cutting through the sphere, it'll define a circle. It cuts out a circle. Well, let's see here. No, let's see. What will it cut out? It'll cut out two lines. It'll cut out a line. Think about the light cone inside the sphere. If you cut that sphere, it'll cut out two lines going in on horizontal lines in the plane that you choose. You understand that? Think about the light cone, a three-dimensional light cone. That's what I'm trying to talk about, and only in terms of rays. We don't want to talk about it in terms of X, Y, Z axis, which are the horizontal and vertical axis. We're talking about the null rays that define the same light cone. And any other point in the plane, you're just choosing a different basis for the geometric algebra 1, 2. And that's what I'm calling the father geometric algebra. Yeah, I'm sorry I don't have better, I'm not better prepared, but we had to come, we just came down here. This is the second week now that we're in Mexico. So, I haven't had access to my normal, but in some way I'm better off. I got more books down here, and I'm having to hopscotch countries, unfortunately.
The blue one circle is the equator of that sphere.
That's right. It's in the plane. That's a three-dimensional plane.
Okay.
So you can see I've got to take that C0 and push it down the other side of the sphere. But I have a better picture, but it's on my phone now. I could send it to you. Maybe I'll do that. I'll send you that other picture. Find it. Let's see. Where is it? Maybe it's. If I can send it to you. Find the damn thing. Let's see, where is it going to be? Oh, okay, I think I have it. So I'm going to try to share that with you right now. And okay, I just sent you the picture. The better picture. So if you can open that, it's a much better picture, really. This is bad, what I said.
I mentioned to Yesus earlier that I have limited time today, so I think that it's probably a good idea if I were to leave the meeting right now. You could continue, and I can view the recording later.
Take a quick look at the picture I just sent you. I just sent it to both of you, and then we'll, like I say, I'd like to meet next week, or some other, whatever. We can meet in 3 weeks too, whatever you want to do. But I will try to get better organized in the meantime. Did you get the
for me?
picture I sent?
I don't have an email from you.
It should come in. Let's see, I'll check it.
No, I don't have anything yet.
Oh.
In my case, my schedule is such that it's kind of busy over the next 2 weeks. So for me, the 24th, in 3 weeks from
Okay,
today,
that would be fine.
would be
for me.
best for me.
It gives me more time to work on this stuff. I've really just had this insight since coming down here. Now my latest insight actually. So I can understand
Okay.
that.
And Jesus, is Wednesday the 24th okay for you?
Wednesday the 24th, it's okay for me, yes.
Yes, okay. So I think we will agree then that we can continue with Dr. Sobczyk's presentation, I think, specifically on this subject. In
By
the
the way,
meantime, also,
I did send a picture, so you should get it. It's just I guess it's 3 megabytes long, and it's a
yes,
little
I
bit
see
big.
something here is received. Yes.
Well, if you look at that picture, it is a better picture. It's more with perspective in it. But that's fine with me. It gives me more. We've got a lot of things we have to do here to get reestablished in Cholula.
Okay. Yes, I received your email, so and I see that it is a somewhat more elaborate drawing than the one that you had shared there.
So I'm going to try to work with these engineers. They're very expert at making pictures. I've been trying to explain these ideas to them, and the thing is that the Fano plane is in 3-dimensional space. That's the next step up, but the plane I've assigned, we're talking about just using rays to find geometry in terms of rays alone. That's all you need, a directed ray. And that's the connection I see with this McLean category theory. And that's what I was hoping that Hayes will be able to, Dr. Cruz will be, and yourself, Bill, that can look at
that comment for me is very controversial, I think. I mean, for me, that would be something like defining set theory in terms of geometry or something like that. It seems like the comparing two things which aren't really comparable. But
look at Greek geometry. Before it was done just with pictures, but then came algebra and geometric algebra. You could do geometry with geometric algebra. I'm looking at category theory in exactly the same way. You're drawing all these loops and
category theory. But maybe I would think perhaps that you're looking at category theory in a very superficial way, right? That the category theory is much more fundamental. Like it's like and that's why I make a comparison with, say, set theory, like something very abstract. Like we don't have to say like a set of what, like a set of, or even how these sets relate to each other, but we're worried about, like in category theory, we're worried about abstract things, like whether or not the set of all sets contains itself, for example. That kind of sort of foundational sort of issues, and category theory was perhaps a similar sort of foundational thing, which is relevant to geometry in the sense that if you want to compare geometry to algebra, you can do that using the language of category theory. But I can't imagine any way in which you could say that category theory can be expressed in terms of geometry. Rather, it's the other way around.
But that's the idea that Dr. Cruz was talking about. The 3 pictures he showed me inspired me to think about it.
No,
where you're drawing pictures of
Yes,
you're drawing
yes,
pictures.
Professor
You can
Garrett,
abstract that a geometric consideration, I believe. That's what we're talking about.
with
Well, for
some,
example, let me just say, the Egyptians invented unit fractions, and they were trying to do all of fractions with unit fractions. Yeah, you can do it that way, but it's not the best way to do things.
no, I think that we need to fix some ideas here, because I was using some graphics for presenting in a pictorial way some concepts, but those pictorial waves are not substituting those concepts. I think that it is important to fix the fundamental ideas of in category theory, because we start with objects and a relation between objects that are morphisms, and we can use graphics representation for this kind of relation. But how you remember, we can use this kind of representation, and we need more elements in this
sorry to interrupt, but I must say goodbye now, and I'll see you both in 3 weeks' time.
Okay.
Okay.
Have a good 3 weeks.
Okay, thank you. Bye.
Yeah, take care. So I guess we can still talk a little bit.
Excuse me?
Okay, you're still on. That's good. So I was going to just say, what is the relationship between knot theory and category theory? I think category theory is used to do knot theory as well, is it not?
Category theory is not what?
What is the relationship to knot theory? The theory of knots, that I think that's done with a lot of people use category theory to explain knot theory too, is it not?
Knot theory is related with topology, and you can define a top category, and then in this top category you can find the relations, the fundamental properties that are in this category, and then you can express those relations in terms of graphics. That one fundamental subject in category theory are the commutative diagrams, but those diagrams are expression of properties in the category. Then
okay.
I think you can express any. The idea is that you can express everything in terms of category, because it is a fundamental way of presenting anything.
Okay.
Anything.
So I would say that maybe we can abstract with algebra a certain part of category theory, which is not available with standard. But like this concept of local duality, I think is a concept which has been missed. So I'd like to see how you can explain it in category theory. That was I think that's very important.
I am trying to understand your idea. If you permit to me to change screen, maybe I can show one.
Okay, let me get rid of this. Okay, I want to stop sharing. I stopped
Yes.
sharing.
One one summary for this the definition of duality in category theory.
Yeah, the idea is how do you express
Okay,
local
here it
duality,
is.
what I call local duality.
A moment, please. Here. Okay. No, sorry. I used, okay. Okay,
That's
now
funny.
is here.
Okay.
You can see this table of duality statement. You can A and B are objects in the category that we can represent like dots, for example, in a graphics. And F and G and H are arrows in those graphics. Then one relation between two objects, A and B, is expressed by an arrow between them. In the left column, you can see the F arrow connecting A and B. And in the dual statement, you can see how the arrow changes from B to A instead of A to B.
In a way, that's just like the duality between a partial derivative and a coordinate or something, you know, the usual definition of duality. That's what I call global duality. But there's
okay.
What I'd like to know is what local duality is in category theory.
If we want to speak of that definition of duality in terms of category theory, we can do that. But then we need to understand first that the partial derivative and differential are vectors and modules in a ring that are part of those algebra. And then we need to define the category of modules and then find the properties there. Then it is not too direct, the association of the concept of duality in between this abstract representation and the common use of duality. I have here sorry for the change here.
Okay, what I'd like to okay, let me just say one thing. What I'd like to understand in category theory is the Fano plane. Have you ever looked? Can you look at the Fano plane in terms of category theory? I think that would be a key to relating the two ideas what we're talking about. The way I'm looking at it, what I call local duality and the Fano plane, I think is very important. So I'd like to see how you would represent the Fano plane in category theory.
Yes, but I need to understand first what are the properties of the final plane in the way
Okay.
that I can
So I think
express.
if you look at that John Baez, I sent you that link to John Baez material. He explains it very well, actually, the way people look at it using, well, a group algebra. But he uses the two p-adic numbers, which is very interesting. So I'm sure that that could be done very nicely with category theory. So that's the part of category theory that I am interested in, to understand how you do the Fano plane with category theory, and that would relate it to what I'm trying to do with local duality. So that would be a key to try to understand these things in a joint way that we both could understand it.
Yeah, but then we need to. I'm going here to stop the sharing. Because I think that in the case of the Fano plane, we need to speak before about this kind of representation of one algebra. And here I think that we need to start with manifolds, not with rings. Because we are thinking here about the peculiar property of that geometry, that is the sphere geometry related with the plane geometry, and I understand this like a special case of the I lost the a special case of Riemann sphere. And I try to understand this in this way. And Riemann sphere, it is too much important because it's the starting point for the complex numbers, and after quaternion and octonions that were
right. So the
introduced.
plane is used for talking about octonions, and of course that's the last field, which is non-associative, of course. That's what the plane, the Fano plane explains clearly how octonions arise, really. But I don't know if you have Lunesto's book. He has a chapter on the Fano plane in the last chapter of his book, Lunesto, which is, I think, very interesting. But let me just say one more thing, is that, you know, in my thesis back in the 60s, I examined what we call the vector manifold. So that's right. I was interested in the manifold we called vector manifold, but it was 10 years after my book with Hessides was finished before it was accepted for publication. And I think the reason is exactly the stumbling block we're facing right now. What's missing is this concept of local duality. People have global duality, which is the duality that you're talking about with category theory right now. But partial derivatives, for example, represent a direction as well. So you can represent a direction by a partial derivative, or as a dot product, as a vector into the gradient operator. But mathematicians don't like to think about a partial derivative. They think that is the proper way of defining directional derivative rather than the engineering way of looking at it as a partial. Not, take the gradient and you dot it with the vector, and that's the directional derivative. Then not as some new concept of a partial derivative. You don't need to define a partial derivative to define a directional derivative.
Yes.
The direction of a vector defines the vector. So I think that's what stopped my book with Hesnes from being published for 10 years. And I think the whole problem is this global duality, which is what people use, versus local duality, which I think is new or not recognized as such. Anyway, so I'd like to understand how those ideas translate into category theory. Okay, but that's right. Category theory is probably much more general than what I'm talking about. But I'd like to understand clearly how it's related, for example, to the Fano plane. Not just as the Fano plane is a plane. It's not, it exists in the plane itself, not in higher dimensional space. Well, that's using the two-adic polynomials, the so-called Galois extension fields. But that's what makes it interesting, because I think those ideas as well can be attacked with this so-called local duality. So again, a ray on a light cone is, I think, the basic concept of direction without using a directed line segment. A ray is just a direction, an oriented direction, and everything should be defined in terms of rays, not in terms of vectors, directed line segments, or however you want to look at it. So, okay, so how do you define a ray in category theory? What is a ray? It's not the same thing as a vector, a line segment, a directed line segment. A vector has a length and direction, but a ray has no direct, it has a direction, an oriented direction, but it has no length.
But I don't know, because you can define a line with a pair of vectors, for example, and you can define a category of vectors.
With a pair of vectors, why do you need two vectors? Just one vector defines the direction.
No, because you can build infinite set of parallel rays.
Okay, but that's a direction though. Just the direction of a ray is independent of. It's just.
Yes.
It's just a direction, no length. It has. Well, null vector has zero length. You square, it's a number which has square zero, which is not equal to zero. That's a point on the light cone. And you can translate that.
Okay, translate in this way. I only need one ray. Sorry, one vector. I only need one vector because
that's
I
right.
am
so a ray is just a direction. That's all. It has no length because its square is zero, or it has infinite length. It's just a ray. It's a point on the. It's a line on the null cone from the past to the future.
Yes, but if you take two different rays, two different rays, there are one relation between these two.
Okay, rays. Yeah. Either the two rays intersect in a point or they don't intersect. If they intersect in a point, then that's the singularity point of two directions from the same.
And I like to say in this that the idea of these two rays are related with the dual concept.
No, It's related, yeah, it's related with duality, but also with local duality. That's what's missing. You don't have a concept of local duality.
Wait a moment, because one ray is related with the partial derivative. Just
I'm not talking about derivatives. I'm only talking about directions. It has nothing to do with the derivatives.
yes, partial derivative give to you direction. Is the direction where
okay, you can think about it that way. That's what I call global duality. But local duality is just a direction, no partial derivative at all. It's just a direction. It's an abstract direction. That's all. It's the abstract concept of direction.
Maybe I can see to you one more one more picture that I use it for represent this idea.
Okay.
A moment, please. Here, I think it is. Okay. Here.
Okay.
You have two scalar fields. One red and the blue one, represented by F and G. And now we can, no, I'm sorry. Scalar, I need more. No, sorry. My iPad is with problems with the energy. Then I need to connect. Wait a moment, please, Professor.
Okay.
No, sorry, Professor Garrett. I get to connect my iPad because it is it was going to cut off. Okay, and maybe if I want to find a better picture in where I have represented different kinds of different kinds of operations in the algebra of scalar fields.
No, I think what is lacking is this concept of local duality. I can explain that better later after I have more pictures and graphs. But I think I can make that a very clear concept now.
Yeah. I can't find one. I have here only some of my slides, and I have not.
Oh, please, I have no way.
Oh. No, sorry, but maybe I can try to explain the idea here in the blackboard.
What I think then is either you use partial derivatives to represent directions, or you use null vectors. That's a point, a line on a light cone.
Yes, because I was I'm going. Can you see this
Yes, I see it. I see it.
the picture?
Yes.
I think that this is a scalar field F, for example, and this is the another scalar field
Okay.
G, and
Okay.
then this are levels of the scalar field. For example, it is level F1, F2, F3, and so on.
Okay.
And I can define here G1, G2,
Okay.
G3. And then the definition of those levels are related with one address that are defined by the condition that make G constant.
Tangent lines.
Excuse me?
Tangent vectors to the curve.
Yes, and then this define this.
Okay.
And for this, I define
The same thing.
this. the same.
Okay.
Okay, but there are different things that are related, two levels of constant G that are this, and this is dg.
Okay. Okay.
And I
Yeah,
have
that's
here,
the standard way of doing analysis. That's what people do to do analysis.
yes, and df here. And if I make the evaluation between df and partial f, this is equal to 1. That is the the evaluation that the evaluation of f. That is the relation between covector and vector.
Okay.
And in this way, this is the dual. Df is the dual of
Partial. Mhm.
or of partial f.
Okay,
Yes.
I understand that. But what is local duality? I don't think you can, that's what I want to talk about, local duality. But that doesn't fit in that picture. And that local duality comes from the idea of a light cone, direction of a light cone, a line on a light cone.
Okay, now we can say, maybe I can use this, but you can say that this is a like cone, like like ray.
Which
This
one? DF or partial F? Which one? Both of them?
yes, this is
Okay.
the right right light, and we can say that partial partial G is time.
Okay. Okay. Can you write this? Can you say DF partial F plus partial F DF is equal to 1? Does that make sense? So I want to say that DF partial F plus partial F DF equal to 1. Does that make sense?
I don't understand your point. Sorry.
Well, that's what I'm doing with the null cone. You see, I write C1, C2 plus C2, C1 is equal to 1. Can you do that with the DF star and partial F? Can you say DF star partial F plus partial F DF star is equal to 1? Does that make sense? Does that mean anything?
And not here, because here is this. Sorry, I'm going to change color. Here, this is equivalent to this. This is evaluation.
Okay. Okay.
And
bracket.
and this is tensor product.
Okay. Okay. So, yeah, okay, so you see what I want to ask. So I want to write partial F, partial G, partial F plus partial F, partial G. I want to set that equal to 1, but you can't do that with that. That's global duality that you're looking at. That's what I call global duality. Local
But
duality is different.
but if I get here, for example, I'm going to add one more. I don't know where now I can add one page here. This was changed. Okay. Sorry. Maybe no. Okay.
No, I think these are very interesting what you're saying. And comparing what I want to do with null vectors or vectors with square 0 on a light cone and what you're doing, there should be a deep relationship between the two ideas that I think is missing because you don't have local duality, what I call local duality. So you should be able to formulate the concept of local duality using this tensor analysis and partial derivatives.
I have one more because I try to understand your idea of local duality, and I think that we need to start with quadratic forms, for example.
We are, when I take this basis C1, C2 up to Cn, that's the basis of the geometric algebra 1, n. You have one vector with square 1 and the other vector square minus 1. That's exactly, it's just a basis of null vectors of the father geometric algebra G1n.
Yes, but I think that we need to see that we are speaking about two kinds of algebras. If you remember the idea of these two kinds of algebras with the one space and its dual, then we can define a duality between these two kinds of algebras. But we can define one more one more concept of duality in one of these algebra, in the algebra of vectors, and then in this algebra of vectors, I remember that Dedekind speak about the complementary bases. And then in the algebra of vectors, we have one base for describing the space, but he introduces a different kind of basis with the complementary basis that is related with the multivectors forms. Then I can use one base, for example, E1, E2, E3, but I can change the description of this space and use one Grassmann product, E1 Grassmann product, E2, and E3. And the description of the space is equivalent with the description.
Yeah, I know you can do it that way, but I'm saying that this concept of local duality simplifies those ideas. And that's what I'd like to concentrate on, this Fano plane, to see what you can say about the Fano plane and the way you're looking at it. Well, that's where John Baez comes in. That what I sent you, study that, what John Baez wrote. That's very nice. And see what you can say about that with category theory. And then we can maybe put these ideas together, because I can talk about the Fano plane using these light cone null vectors which live on a light cone. I think we can proceed from that idea. So if you can understand better the Fano plane with well, however you want to look at it, with vector the vectors in the dual space, but I think we can make progress. Maybe if you look at the Fano plane, it's extremely interesting, really. And John Baez, I think, uses the usual concept of duality to talk about that. That's what his paper's about, and uses category theory terminology, which is, I think, that you can appreciate that.
Okay, then I'm going to see your sorry, I changed the camera in my iPad without and maybe you were seeing nothing.
No, I saw your pictures. They're very nice pictures.
Okay.
But no, I understand what you said. Your partial G and DF, DG and D partial G and so on. No, I understand those ideas, but I think you should try to understand the Fano plane by what John Baez does with group algebra. It's not that difficult to understand. Well, it needs a more sophisticated. He's not very sophisticated in his way of explaining it, but he does indicate how category theory comes in to the Fano plane, understanding the Fano plane using category theory. And of course, it can be generalized to higher dimensional spaces. Well, that's related to 2 to the 3 power p-adic numbers, 2 8-dimensional p-adic numbers, as they call it. Which anyway, so that's, I think, a way of it, trying to understand the relationship between what the 2 different ideas we're talking about.
Okay, I'm going to see the reference that you say to me, and
John Baez. That's very interesting. I sent you a link to that. Also, I will write to you directly with some pictures, and in the next week or 2, before our meeting so we can see where we are, where we are at.
Okay. Okay, you say a meeting before that or meeting with the professor.
Yeah,
Pedro?
well, I'll exchange some emails with you. We
Okay.
can communicate with emails.
Okay.
I don't know exactly how to straighten out this, why I'm having this trouble with, with Zoom on my computer here. I did reinstall the new version, but something's not right still. I have to use my tablet at the same time as my computer.
Okay. Okay. Okay, and then we can stay in contact. I am going to review the reference that you sent to me, and maybe we can fix those ideas.
Oh, good.
Mhm.
Yeah, Feliz Reyes Magos.
Igualmente, profesor Garrett. Feliz fin de semana.
Estoy muy feliz hacer en México otra vez. Mi esposa está conmigo ahora en Puebla, en Cholula.
Yeah, and I said to Professor Pesh that okay, Puebla is not so far from here, but I need to organize maybe a complete date for meeting you there in Puebla, because I think that I need around 2 hours or more for travel. Mhm.
Yes, I know.
Yes,
That's a
but
long way. Not so long,
maybe
but
we can meet now that you are here in Mexico. Mhm.
yeah, I will be here till the 28th of January. Then
Okay.
but I have to go back
Oh,
to South
okay.
Carolina. So maybe we can do something. We can arrange something. That would be very good. I'd be very happy to do that.
Okay, thanks a lot. Then I am trying to organize.
Yeah, we could meet at ULA. I do have access to ULA. We could maybe arrange a meeting at Universidad de las Americas or something.
Okay, perfect.
Okay.
Mhm. Okay, then I see you. Oh, okay, we stay in communication.
Yeah, Feliz Reyes Magos.
Bye. Yeah.
Okay, take care.
Yeah.
Adios.
Adiós. Bye.